Welcome. Previously, we covered solving linear inequalities. In this video, I'd like to show you some examples of quadratic inequalities. Like quadratic equations, inequalities can be solved by applying similar rules and steps. Remember to change the inequality symbol if it involves an operation of multiplication or division by a negative number. First, write the quadratic expression in standard form. Next, solve the equation to find the root. Try to use the factoring method whenever possible. If factoring is not possible, we can use the quadratic formula instead. Thirdly, create your intervals using the roots. Then find out each sign of the quadratic expression for each interval using test points. I will use a sign chart for this purpose. Finally, identify the intervals that satisfy the inequality and write the solutions. Let's take a look at the first example. Notice that this is not in the standard form. Let's move the constant 8 to the left side and try to factor the left side expression. Write two sets of brackets with x. Then we need to find two numerical values p and q such that the product of those equals the constant c, and the sum of those should be the coefficient of x, b. In this case, the product of pq is negative 8, and try to find p plus q equal to negative 2. First, try to find the factors of 8. Since the sign is negative, two numbers must have the different signs. We can try 2 and negative 4, which gives the product of negative 8 and the sum of negative 2. This value matches the coefficient of x. Let's place each value inside of each bracket to complete the factoring process. The order of each factor could be reversed, of course. Then find the roots by letting each factor is equal to 0. We found two roots as negative 2 and 4 in this manner. Let's make use of these roots to create the intervals. The intervals are less than the smaller root negative 2, between negative 2 and 4, and larger than the larger root 4. Then pick up test value for each interval. Using the sign of each factor of quadratic expression to determine the sign of the original expression. Substitute the test value of negative 3 into the factor of x plus 2 to get a negative. Likewise, substitute the negative 3 into the other factor to get a negative as well. Multiplying the two negative signs to get the positive for the quadratic expression. In the similar way, we get negative in the second interval and positive for the last interval. Now we found the sign of the quadratic expression for each interval. The question asks to find a negative region. So the inequality is less than 0 between negative 2 and 4. The solution in an interval notation is as shown. Let's check to see if our solution is correct. Pick a value between negative 2 and 4. For example, x equals 1. Substitute this value x equals 1 into the left-hand side of the original inequality. and we get -1, which is indeed less than 8, which means our answer is correct. Here is a graphical representation of the solution. For your reference, if quadratic expression is less than or equal to 0, then our solution should be between the two roots, like this example. However, if it is a positive case, the interval should be less than a small root or greater than a larger root, as you can see them on the graph. Please note that OR means the union of two intervals. Let's go back to the solution for this problem. Let's take a look at another example. We can see the negative leading coefficient. We divide the entire inequality by -1 to make the problem simpler to handle. Since we divided both sides by negative number, we need to make sure to change the direction of inequality symbol. Now we try to factor the left side of the expression. For the first term, think about the factors of 2x squared and place each factor 2x and x underneath. Next, move to the last term. Find the factors of 6. Since the sign is negative, either factor should be negative. Say 6 and a -1. Then we cross multiply to get 6x and -2x. However, the sum of those must be 11x in the middle term. And to have the positive sum, let's switch the factors. Again, double-check the sum by cross multiplication. We have 11x this time, which matches the coefficient of the middle term. Write 2 sets of brackets to have the factored form. Let's set each factor to 0. From the left factor, we get x equal half. Solve the right factor to get x equal -6. Let's make use of these roots to create a sign chart. Please make sure to place those in numerical order as a number line. In other words, the smaller number should be written first. The intervals are less than the smaller root -6, between -6 and a half, and larger than the larger root half. Then pick a test value for each interval. Using the sign of each factor in the quadratic expression to determine the sign of the original expression. Substitute the test value of -10 into the factor of 2x minus 1 to get to negative. Likewise, substitute -10 into the other factor to get to negative as well. Multiply the two negative signs to get the positive for the quadratic expression. Similarly, we get the negative in the second interval and positive for the last interval. Now we found the sign of a quadratic expression for each interval. The question is to find the positive or equal to 0 region. So the inequality is positive, less than -6 or greater than 1/2. So the solution in an interval notation is as shown. The union of two regions. Please note that the square bracket means that -6 or +1/2 is included on an interval. Let's check if our solution is correct or not by using the original inequality. Please note that the original inequality shows less than or equal to 0. Again, pick a value less than or equal to negative 6, say x equals negative 10. Substitute x equals negative 10 into the left-hand side of the inequality, and we get negative 84, which is indeed less than 0. Let's pick a value from the other region, say x equals 1 this time. Substitute x equals 1 into the left-hand side of the inequality, and we get negative 7, which is less than 0 as well. Both have checked the solution. This is a graphical representation of the solution we just found. Next, we will explore examples of double or compound inequality. There are two methods to solve this type of problems. The first method involves solving all three parts at the same time, and the other method is solving two separate parts independently. Let's try to solve a double inequality problem. First, let's make two inequalities according to the rule. Starting with the first one, we add 6 on both sides to get x squared minus 5x plus 6 is greater than 0. Let's factor the expression. We write two sets of brackets with x and try to find two numerical values p and q such that the product of those equals the constant c, and the sum of those should be the coefficient of x, b. In this case, the product pq is 6, and try to find p plus q equal to negative 5. First, think about the factors of 6. Since the sign is positive, two numbers must have the same signs. Since the sum is negative, two numbers must be negative in this case. How about negative 2 and negative 3? This combination gives the product of positive 6 and the sum of negative 5. This value matches the coefficient of x. Let's place each value inside of each bracket to complete the factoring process. Then find the roots by letting each factor is equal to 0. We find two roots as 2 and 3 in this manner. Let's make use of these roots to create the intervals. The intervals are less than the smaller roots 2, between 2 and 3, and larger than the larger root 3. Then pick a test value for each interval. Using the sign of each factor of the quadratic expression to determine the sign of the original expression. Substitute the test value of 0 into the factor of x minus 2 to get the negative. Likewise, substitute 0 into the other factor to get negative as well. Multiply the two negative signs to get the positive for the quadratic expression. Similarly, we get the negative in the second interval and positive for the last interval. Now we have found the sign of the quadratic expression for each interval. The question asks to find the positive region. So the inequality is positive, less than 2 or greater than 3. So the solution in the interval notation for the first part is as shown. The union of two regions. Set this aside and we solve the second one next. Let's solve the second inequality then. Move the constant 6 from the right side to the left side to get the standard form. Again, we first attempt to factor the expression. Write two sets of brackets with x. Then we need to find two numerical values whose product is -6 and whose sum is -5. First, think about the factors of 6, which has a sign of negative. So two numbers must have different signs. How about +1 and -6? This combination gives the product of -6 and the sum of -5. This value matches the coefficient of x. Let's place each value inside of each bracket to complete the factoring process. Then find the roots by letting each factor is equal to 0. We found two roots as -1 and 6. Let's make use of these roots to create the intervals by making a table. The intervals are less than the smaller roots -1, between -1 and 6, and larger than the larger root 6. Then pick a test value for each interval. Use the sign of each factor of quadratic expression to determine the sign of the original expression. Substitute the test value of -2 into the factor of x plus 1 to get negative. Likewise, substitute the same value into the other factor to get negative as well. Then multiply the two negative signs to get positive for the quadratic expression. We get the negative in the second interval and positive for the last interval. Now we have found the sign of the quadratic expression for each interval. The question for this part asks to find the negative region. So the inequality is negative between -1 and 6 inclusive. The solution in the interval notation for the second part is as shown. We have one solution set from the first inequality and another solution set from the second part. We need a final solution for the problem by combining these two solution sets in the next step. Here is a graphical solution set of the first part. And this is a solution for the second inequality. Please make sure that we need to combine these two sets of solution with AND, which means intersection. We prefer to represent both solution sets as a number line to see the intervals easily. This dark red lines show the interval solutions for the first part, and the red line indicates the interval solution for the second part. Now we need to find the intersections of the two sets. We can see the common intervals of the two lines are between -1 and 2. -1 is inclusive, but 2 is not included. Also, the other common intervals of the two lines are in between 3 and 6. Again, 3 is not included, but 6 is inclusive. Now we have the final solution in two regions. These regions must be combined with OR, which is the union of the two sets. Therefore, the final solution in an interval notation is shown. Here is a summary of what we have learned so far. First, rearrange the inequality so it is in the standard form. Next, factor the inequality expression and find the roots. Then identify the intervals that satisfy the inequality by using test points in a sign chart. When you have time, then please check the solution. Quadratic inequality can have infinitely many solutions, one solution, or no solution. Please practice many questions after watching this video to become more comfortable with inequality questions. Thank you for watching. See you again.